output are 0 for a batch reactor. Here there is an input through diffusion, a slight complication is there. So, accumulation is equal to rate of production, that is these reactions. Now, charge cannot be accumulated, you see sometimes 0 there, and there is a rate law which I have described to you. Conduction is there by Ohm's law. So, these are things which you can learn, they are not very, very difficult. Ionic conductivity, they are all things which you learned in physical chemistry. So, these balances can be written. So, these are the design equations. These are the design curves for battery. Let me explain to you because you have not seen them before. Here I plot voltage of the battery as a function of the current I get from the battery, as a function of the capacity I am drawing from the battery. When I am withdrawing current from the battery, I am getting so many coulombs out. So, as I take more and more coulombs out, then the voltage drops. Like your lithium battery in your cell phone, charge now. What happened to it is, voltage has gone very, very low, you can't work with it anymore. So, you got to put charge. So, as you withdraw charge, voltage falls. This current density is written in a particular way. This C is the theoretical capacity of the battery. Suppose I discharge the battery in 20 hours, very, very slow rate of discharge, then current is called C by 20. I can calculate the current from that. I am discharging so many coulombs in 20 hours. You know, current is coulombs per time. I have the current density. So, I can easily calculate that. So, C by 20 is very, very slow discharge because I am trying to discharge C in 20 hours. 6C here, okay, I am discharging the battery in 1/6 of an hour, only 10 minutes, really super fast. Okay. So, you plot this voltage versus capacity drawn as a function of current density. The battery, this battery has got 4 amperes per kilogram. Okay. Now, when I discharge at C by 20, I get full capacity. When I do 6C, I am only getting one unit out. How do I design a battery? You want 4 ampere hour at 6C. What you do is you take 4 batteries. So, battery becomes bigger and bigger. That is how you design a battery for car. A car should give you lighting, that is good, very low discharge, but you want to start the car. It will draw a hell of a lot of current at that time. Therefore, you must give 3 batteries which you see in the car for this reason, just to account for starting. For lighting, nothing at all. This is how these curves are used to design batteries. Maybe you can't see this here. These curves have come, there are many, many curves, but these curves have come from a paper in 2010. Okay. Now, chemical reaction engineering approach is to predict these design curves. That means, I must solve those mass balance equations and predict these curves. There is one parameter which I showed you, reaction rate constant. I can fit this reaction rate constant with C by 20. If I try to predict the curve at C by 6, it won't. That is not good, because chemical reaction rate is a fundamental parameter. How can it depend upon the discharge rate? So, even in 2010, there were empirical attempts which are made to predict these curves. So, I wanted to see whether chemical reaction engineering approach will give us the results or not. Why it should not give us the results? It should give, if it can work for chemical reactors, why can't it work for batteries? What is special about batteries? Also a chemical reactor. So, this is what I call fouling of a battery. This is my explanation for you. Sulfate particles are forming. They must follow the classical nucleation growth path. There is no other path. It must nucleate and form particles on the surface of lead or lead oxide. Okay. So, increasing current density means I am increasing the rate of reaction. I am drawing current very, very rapidly. That means, I am producing electrons very fast. That means, I am making the reaction go fast. That means, I am producing lead sulfate very fast in solution, because lead sulfate can only form in solution. So, what am I doing? Like in the case of gold particles, I have used a chemical reaction to produce the product at a very rapid rate. So, what happened in the gold particle case? Supersaturation got built up very, very rapidly. Therefore, nucleation rate increased. So when I am trying to draw current very, very rapidly, I am nucleating particles very, very rapidly. That is the first effect. So increasing current density increases rate of formation and therefore number of nuclei. So for a given conversion, I form many, many particles. Many, many particles are now sitting on top of these particles. So if at low current density particles are like this, at high current density more particles are there covering more and more area. If more and more area is covered, what happens at rate? The blocked area now, okay, the blocked area is not useful anymore. Therefore, it's completely blocking the surface, is not able to give me as much of current which I want to draw here. Okay. So I want to predict these design curves. Okay. I'll take a little bit of time to explain this to you. It's not very difficult. These parts are intrinsic parameters, how voltage difference activates. Okay. That's normal. Similarly, how concentration, first order, second order, they are molecular parameters. Nothing is going to change. I can only deal with this fouling factor as to how the area is getting deactivated. Okay. That's what I have to explain based on the nucleation growth model. There is one effect which is not in chemical reaction engineering. I got this lead and lead oxide particles. They are reacting. So what happens to the volume? The volume must decrease. If the volume decreases, the area also decreases. Therefore, first effect is the area of the active particles is decreasing. Okay. So suppose U is a fraction converted. Okay, like your X, capital X in Levensspiel, U is the amount fraction converted. Therefore, 1 minus U is what is left. 1 minus U is the volume left. What is the relation between volume and area? This comes from Buckingham pi theorem. Volume is length cube, area is length squared. Therefore, area decrease must be 2/3 power of the fraction converted. But the initial amount I started out with A naught. Therefore, fraction decrease is A naught into 1 minus U to the power 2/3. You see how simple this is. This is where chemical engineering is so nice, because you can apply your basic ideas and figure out fairly complex things, provided you got a physical insight. How things are happening, you must imagine and have this insight to quantify them using simple dimensional arguments. Okay. Now, I want to calculate, bring the effect of nucleation and growth. Okay. So, this is the first term which I already shown you. From U, don't worry about these minor factors, they can be easily understood. U is a fraction converted. So, if I know how many moles of reactants I have started out, I can multiply that by U, get the moles of product that are formed. Very simple. Okay. From the moles of product that are formed, I can calculate the volume of the product formed by multiplying with the proper molecular density. This is the total volume of the product that has formed. I divide that by number of particles. Okay. Like I told you about the gold also. I took the initial amount, divide by the number of particles to get volume per particle. So, this I divide by number of particles, I get the volume per particle. 2/3 power area of particle multiplied by the number of particles. That is the total area of the particles. Okay. Some fraction is there. So, that is at C. Okay. How do I get N? Number of particles formed. I got this nucleation theory which I told you. I apply the same theory to calculate the number of particles formed. Same thing, no difference at all. Supersaturation, I know the solubility of lead sulfate. Concentration in the solution, I know the reaction rate. Just the same mass balance which I showed you for a batch reactor. I do the same thing. Rates are different, nothing else. Once I get those things, I apply this blocking formula and I calculate whatever I want to calculate. So, if you have a catalytic reactor and you are fouling, you do this. You can do the same thing. I don't know if anybody has done it or not. It should be possible. You want to know how heat exchange is fouling? Very simple. You calculate the nucleation rate, where is depositing, how the surface is growing. You get fouling. You wonder whether I am getting a heart attack or not. Arteries are getting fouled by cholesterol deposition. Okay. Calculate how they are growing. Apply nucleation and adsorption model. In principle, I should be able to tell when I will get a heart attack. I need to know a lot of parameters, but it is possible. I want you to see there is a chemical engineering template here. You look at it from the viewpoint of a chemical engineer, any phenomena. Okay. And you can use very, very simple ideas and to fairly complicated calculations you can make. Here plus nucleation growth rate. And C by 20 good, C by 5 a little bit, C by 1 okay, 3C okay. 6C I was computing as I was coming here and a little bit more deviation is there. Okay. Where can this deviation come from? One is that when particles are growing, I assume they are growing on the surface. Here is a particle sitting on surface. But when it grows, it can hit on the other particles. I am growing big and big. I got 2 walls here. I am thinking I am here, but I have become fat. I am blocking this wall also. So, there is a little bit more complexity in figuring out the blocking part of the area. My model is very, very simple. It is first cut as they call, but I need to do a little bit more to actually calculate what exactly happens. Now, 6C I need to fix. I am very confident I can fix it. Okay. I have very, very famous quote from Professor C.V. Raman. He said, a scientist lives in the hope of making a discovery tomorrow. So, I hope I can solve 6C and 10C tomorrow. Okay. Now, these are my conclusions. Fundamentals of chemical engineering are evergreen. I learned my chemical reaction engineering in 1960. Okay. 50 years are gone. I use the same knowledge. I showed to you. I use the same knowledge which you read in Levenspiel. I have not used anything more. I learned about nucleation. You can't be not learning anything new. You have to learn something new. But you use your very basic things and you can come to very classical areas and also very modern areas. I dealt with nanotechnology. I dealt with batteries. Okay. Lithium batteries, same principle also can be applied. So, as long as you are able to learn your fundamentals well and learn a few new things, whatever you learned 50 years ago, someday you will also be 50-year-old. So, at that time you also can apply these things still. Nucleation growth of a new phase is central to well-known unit operations. I gave you examples in the beginning. It is also applicable to nanotechnology and electrical energy storage. Chemical engineering models can provide insight into control of gold nanoparticles and also about fouling. I want to leave you with one more idea here. Suppose I do develop this model. What do I do with it? What should I do with it? I predict curves. Okay, not good enough. I should tell now how this model can be used to make the battery perform better. Okay. So, I have got a senior colleague whom Sherry knows, Santosh also knows, Professor Kumar. He sits right next to me. So, I keep on discussing with him, what should we do? So, he had an idea. The idea is I seed the battery with particles. Here is nucleating when production is taking place. That is random. What I do is I create seeds at the right places. Then lead sulfate will go sit there. Very nice idea. You can control particle size, you can control fouling. This is how a model has to be used to tell what can be done, how to rectify a process. Similarly, Sanjeev has got this control, how to control particles. Then he used how to generate them on a continuous basis and a fairly large scale. That is when a model is fully used. Model is not just predict curves. That is very, very important, no doubt. But it should give you an insight which will allow you to control the process, to make the process better. Now, I promised to you, I gave you my humble example. This is very, very easy. I want to show you something more inspiring. I told you I'll show you more inspiring examples. I got a couple of them here. This gentleman here, I don't know how many of you can recognize him. I doubt it very much. This is Dr. Andrew Grove. He is one of the founding fathers of Intel, the giant which designs and makes electronics chips. He is a chemical engineer. Okay. He did his PhD on mass transfer in boundary layers. And he wrote a beautiful position paper on mass transfer in semiconductor technology in 1966. A lot of it is outdated now because technology has moved on, but I want you to go and read this paper. It's beautifully written. Okay. It tells you the breadth and the depth of thinking that is possible. I don't think anybody will recognize this gentleman here, but I am very sure all of you recognize that. That is a medal which accompanies Nobel Prize. Okay. This gentleman is Professor John Fenn, who taught chemical engineering in Yale University between 1981 and 1994. As far as I know, he is the only chemical engineer who wanted to learn the basics as well as you can and apply them, learn to apply them to whatever, how you digest food, how blood flows in your blood vessels, whatever may be there's a lot of chemical engineering in everyday life. You try to apply those things which you have learned to those daily life examples and you will learn a whole lot. I like to end by thanking Dr. Chopra, who is not here, for making this possible for me to come here and give this lecture. I find this audience so very receptive. I feel charged up like a battery. And I thank Professor Srihari, Professor Santosh Gupta for making this lecture possible, make my visit very, very comfortable and very, very enjoyable. And finally, all of you heard my talk in great patience, and thank you all. Thank you very much.
Once again, we've had such a delightful talk. I'm not surprised. Me and Gandhi, when Gandhi was at IIT Kanpur, right till 84, right, we shared this.
Nanoparticles here, like acid particles. I just want to know the application of gold nanoparticles.
I will give you two examples.
Yes, sir. Yes, sir.
Yeah, one is about radiation treatment for cancer. So what they do is, these days you know radiation has got collateral damage. So not only cancer cells, but neighboring cells also get killed. So what they would like to do now is to really focus the radiation beam exactly to the spot where cancer cells are. So what they do is they embed the tissues with gold particles by injection or various methods. Now those gold particles are sitting on cancer cells. When one goes to take radiation treatment, they image these particles. Therefore, they know exactly where the cancer cells are there and direct the beam to those things. Another thing is analysis. You can analyze DNA fragments by functionalizing gold particles.
So the lead sulfate that is forming in the lead, that is precipitate. Can we do anything using nanotechnology or is there any idea for the lead sulfate to be?
Yes. Not perhaps in the way you are thinking, but nanoparticles, a lot of people are trying to use nanoparticles. The reason very simple. I multiply the heterogeneous reaction rate constant with area per unit volume. If you got a nanoparticle, you got a huge amount of area per unit volume. So people are trying to make lead sulfate, lead oxide and lead in nanoparticles so that you can get discharge rate by improving the area. Second thing is the particles you form are still very small, therefore recharging them can also become very small. So lots of people are trying to make reactive materials in the form of nanoparticles lead sulfate. In lithium there is a different application. Many people including Professor Ashutosh Sharma in IIT Kanpur, they want to make electrode substrates using nanofibers. They are support, so nanofibers will give you a lot of adhesive area and also more porosity by packing more area per unit volume with lot of voidage, so diffusion can become faster.
That's a hallmark of a good teacher, no questions.
Either it's very clear or it went over the head, so we don't